In the lecture for Deutsch-Jauser algorithm, we have seen that the QuTalent algorithm achieves exponential speedup over the classical algorithm. In this lecture, we are going to study another algorithm proposed by Grover in the year of 1996, which helps us in searching tasks. Hence, it's sometimes called the Grover search algorithm. The task that we would like to address is that given an unstructured database which has n objects, how could we find the object of interest? For the purpose of illustration, I'll just assume there's one object of interest that we are searching. Of course, the algorithm can also be generalized into more than one object that we are searching. Let me first explain what do I mean by unstructured database. Suppose you go to the library and you are looking for a book. The books are arranged in different sections. So there are the section for the science book, there is the section for the math book, for example, and there is the section for the fiction book. So in this kind of database, the object has a structure. For unstructured database, the analogy would be a blind lucky draw. So for example, I've drawn n boxes here for the n object. Only inside one of the box, there is a prize. So you can see a candy over here. So how can we find this box with the candy inside? If all the boxes are identical and all that you are allowed to do is to just open the box and check whether there is a candy inside. So there is no structure in this database because all the n objects are distinguishable, they all look the same. Your best strategy will just be open one by one until you find the candy. In this lecture, we're going to see that using the Grover search algorithm, the QuTalent algorithm achieves quadratic speedup over the classical algorithm. Although the speedup is not exponential, this algorithm is very important because it has practical applications. Searching is basically ubiquitous in our everyday life. For example, as I said, we can go to the library to search for a book, or you want to search for other things. So let us see how we can formulate this problem. So for that, first I'm going to turn this into the function description, where I'm going to describe this 0, 1, 2 to n minus 1 as my input and my output 0 or 1. If I found the object of my interest, so f of x will be equals to 1 if x is the index that I'm searching for, or just the object that I'm searching for. Otherwise, the function will be equals to 0. It is often convenient, as we have seen in the Deutsch-Jauser algorithm, to denote this n object rather than counting from 0, 1, 2 all the way to n minus 1 as an n-bit string. So I will equivalently write this as the input is a n-bit string 0, 1, n-bit, and the output is 0 or 1. So here, our task is basically to find this box that contains the candy So we have to find this W. As we have seen before, in the classical algorithm, which is basically a brute force searching algorithm, the order of this problem is n. This is because you have to open on average about half of the boxes. Sometimes, if you're lucky, maybe after opening a few you found candy, but sometimes you may be unlucky, you have to open quite a lot of the boxes. So on average, you have to open about n over 2 number of boxes, so we say the order of this problem is n. Now, how about the QuTalent algorithm? In this lecture, we're going to see that the order is the square root of n. So here there is a quadratic speedup over the classical algorithm. This speedup, although it's not exponential, but for large value of n, this is still a considerable speed up. So before we show that, let us first turn this problem into the content description. So in the content description, as we will usually do, is first to change the n bit. So here the big N and small n are related to each other. This capital N is 2 to the power of the n. So here we have n bit. We're going to turn this into a n qubit register. So the n bit will be replaced by cat, where this cat x is an n bit string, but this we will assume is an orthonormal basis. So for example, if we have small n equals to 3, for 3 bits we have 8 boxes, so we can use 3 qubit register, and our orthonormal basis will be the usual 0, 0, 0, 0, 0, 1, all the way until 1, 1, 1, altogether 8 basis cat. We will further assume that there is an oracle, which sometimes is also called a subroutine. Let me call it U of W, that help us to identify the object of interest. So how does it do that? As we have seen in some other algorithms, such as the Deutsch-Jozsa algorithm before, corner algorithms make use of constructive or destructive interference by manipulating the phase in front of the different cats. So for example here, what it can do is that, suppose this is the object of interest, it's going to change this phase to +1 to -1 for our object of interest. But for all the other, it just leave it unchanged. So at this stage, for the purpose of this illustration, we will just assume there is an oracle that does this for us. As you can see, this is actually a unitary transformation, so it can be realized in the lab. For now, we will not worry about its actual implementation in the lab. These two sentences can be actually more compactly written as U of W acting on X is equals to -1 to the power of f of x. So for the object of interest, that is equals to 1, we pick up a phase of -1. Otherwise, for the rest, we just get 0 here, so there's no phase change. As -1 to the power of 0 is 1. So this is what the oracle does. Finally, how do we model this scenario of an unstructured database where the object of interest could be equally likely to be found in any of these n boxes? So to model that, we will prepare our initial state in the equal superposition state, which is the sum over all the basis cats in the orthonormal basis. So here my sum goes, I'm using the n-bit string value notation of 1 over root n of all the basis cat over here. This equal superposition correctly models the problem over here. As you can see, since the candy is equally likely to be found in any of these boxes, so if you randomly open one of the box, your probability of success is 1 over n, and of course the probability of failure will just be n minus 1 over n. And this is exactly shown in this equal superposition state because each of the basis cat occurs with the amplitude 1 over square root of n. So for example, the overlap between the W cat, which is what we would like to find, with the equal superposition is 1 over square root of n. So its square will give us the correct probability over here. One final remark before we move on. Although the oracle helps us to identify the W by flipping its sign, it does not help us find the object, because as you can see here, even after the action of this W which changes this phase, the probability of finding the state in the W is still 1 over n, which remains as before. Before we look at the implementation of the algorithm and its content circuit, I would like to show you a geometric visualization which helps us to intuitively understand this algorithm. To see that, let's remind ourselves that in this equal superposition state, there is the state W, which is of our interest, and all the rest. So let me call that x not equal to W. I'm going to rewrite this part a little bit as, so this is the part that we want. And I'm going to call this part, so there are n minus 1 of them. So to properly normalize it, so I have 1 over square root of n minus 1 x, and this sum over the x not equal to W. So then there is the n minus 1 over n with the square root in front. And I will just denote this part as W tilde. So here you can see that the W and the W tilde, the overlap is equals to 0 because the W is orthogonal to each of the component in the W tilde. And the overlap between the S and W is 1 over square root of n, and the overlap between S and W tilde is n minus 1 over n square root of that. So effectively, the W and W tilde forms a two-dimensional subspace, and I'm going to represent that geometrically here using two vectors which are orthogonal to each other. So this is my W tilde, which has much more overlap with the S, and this part is the W, which has only little overlap with the S. So initially, my equal superposition state is very far away from the W and much closer to the W tilde, and this angle is very small when we are searching for a large database which has a very large number of objects, so for the n to be large. I'm going to denote this angle here by theta over 2. Okay, so now suppose we're going to do a measurement. The probability of obtaining the W is just given by the square of this overlap, which is 1 over n, as we have seen before. So how are we going to increase this probability? From this picture, you can see that the idea is that we hope to do a rotation of the equal superposition state towards the W such that the overlap between the final state after the rotation with the W will become larger and larger. How to achieve that? It turns out this rotation is done via two consecutive reflections. So first of all, we're going to reflect the state S about the axis defined by the W tilde. So that will turn the state over here. And this is exactly the action of the oracle. So this state will be UWS. Because as you can see, this reflection does not change the overlap between the S and W tilde, but it flips the phase. Originally, the overlap between the S and W is a positive value, but after the reflection, it becomes negative. So this is exactly what the oracle does that we wrote down before. So this is the first reflection, and this angle is theta over 2. And now we want to do the second reflection to bring this state closer to W. So you can see we can do that via a reflection about the axis defined by the S. So I'm going to reflect this about the state S. So this angle is theta. So after reflection, it will be another theta over here. Okay, so the second reflection is done with the help of what is called the Grover's diffusion operator that we will learn later. But now let me just denote this by U of S. Acting on this state, which is U of W. And let me just call this a Grover iteration, so G of S. So one iteration consists of two consecutive reflections. The first reflection about the axis defined by W tilde, and the second reflection is about the axis defined by S. So first and the second. So this is one iteration. So as you can see here, after one iteration, the state S become g of s, which is closer to the w. And we can continue to do that. So let me do it one more time. So first I'm going to reflect this state about w tilde. So this angle is altogether 3 theta over 2. So it will become here 3 theta over 2, but there's already a theta over 2. So that means the state will become here with the angle of theta here. Alright, so this is another action of the u of the w acting on g of s. And then I'm going to reflect this about the s. So this is 2 theta. So that go to theta over here, but there's already no theta. So it will go over here. So this is another theta. And this state will be, I've applied this Grover iteration twice. So this state will be g squared acting on the state s. Now, we can see from this geometric visualization that each iteration brings the state s theta, the angle of theta, closer to the w. So 2 iterations, this angle will become 2 theta. So after a few times of iterations, where the number of optimal values is to be found, the final state will be very, very close to the state w. Eventually, what we would like to achieve is that after a total of k iterations, we would like to have this angle close to pi over 2. So initially the angle is theta over 2. After k iterations, this angle will become theta over 2 plus k theta, because every time we will bring this angle theta closer to w, and we would like to have pi over 2 for this. So let us remind ourselves that theta over 2 is the initial overlap between the w and the s. So this number is equals to sine of theta over 2. We are discussing the case of large value of n, so this is a small angle. So on the small angle, sine theta over 2 is approximately equals to theta over 2. So the theta over 2 is just approximately equals to 1 over square root of n. So here, then we will have 1 over square root of n plus k times theta. So that's k times 2 over square root of n. And this is going to be close to pi over 2. So moving this term over and multiply by square root of n over 2, we can find the optimal value of k. So upon solving that, we will see that k is given by, we will have pi over 4 square root of n minus half. Okay, so for large value of n, this is just approximately equals to pi over 4 square root of n. So the optimal value for k, as we can see from the result over here, is of the order of square root of n, which is what we have claimed before. Using the compound algorithm, the order of this problem is square root of n, which is a quadratic speedup over the classical algorithm. We are now ready to draw the coupling circuit for the Grover search algorithm. First, I will just claim that the oracle is given by uw equal to the identity minus 2w ket w bra. This is very easy to verify because you can check that, remember our uw acting on the state s, which the s is 1 over root n w plus n minus 1 over n square root of that with the w tilde. And what we would like to achieve is to leave this part unchanged and change the phase in front of the w from plus to minus. So if you apply this oracle over here, the identity leaves this part unchanged, and this part acting on here will give you minus 2 over square root of n of w, and this part will give you 0 because w and w tilde are orthogonal. So after that, you will just get minus 1 over square root of n of the w plus the rest are unchanged, which is exactly what the oracle achieves for us. So this is the oracle, and this achieves the reflection about the axis defined by w tilde. After that, we need to do a Grover diffusion operator. So in order to realize the Grover diffusion operation, the operator is given by 2s minus the identity. Again, you can check for yourself easily that this does a reflection about the axis defined by S. We are now ready to draw the quantum circuit for the Grover search algorithm. So to prepare the equal superposition state, we first have the 0 n-qubit register being acted by Hadamard gate. Each of the qubit is acted by the Hadamard gate. So here we have 0, H tensor n. And after that, we do the Grover iteration for an optimal number of times. And this optimal number is the k that we found before. And after that, we just do the measurement. Okay, so the Grover iteration is made up of 2 steps. The first step of the oracle and the second step by the Grover diffusion operator. So the G over here is the same as first the action of the oracle. Okay, and so all these are n-qubit. The Grover diffusion operator. Before I draw the Grover diffusion operator, so let me again remind you that the S is given by Hadamard tensor n acting on 0 tensor n. So I can rewrite this part a little bit by H tensor n is 2, 0, 0. So the 0 here actually means 0 tensor n, so it's a short notation to mean all the bit string inside is 0 minus the identity followed by H tensor n. So you can check this part acting on the 0 cat give you the S cat. This part acting on the 0 bra give you the S bra. So this together will give you this part. And for this part, identity with the H and H, but H with H give you identity, so this part just give you the identity. So in order to realize the Grover diffusion operator in the lab, we actually do it via 3 steps. The first step is the Hadamard gate, n of 10, followed by this operation, which is also a conditional phase shift. So you can verify that this conditional phase shift leave the phase for the 0 state unchanged and flip the phase of all the other states not equals to 0 from plus to minus. And finally, another Hadamard tensor n. So this part over here, the action of this 3 realizes the Grover diffusion operator. And this is a conditional phase shift. Which we can actually implement in the lab. Alright, so to conclude our discussion, I would like to mention one more time that the K is given by pi over 4 square root of n. So we can see that in the case of the quantum algorithm, we achieve a quadratic speedup as compared to the classical algorithm.